Hello everyone, welcome to another episode when I do a reconstruction of the game of Go written by Jonathan KIM-1 in 1981. And there was an article in the Byte magazine in April 1981 describing this exact program, how it can be coded, but without particular source code, just providing the bare pseudocode and some explanations how to approach making these programs. So last time I was really confused with the fact that when I was trying to put a stone on board somewhere, like in here for instance, and I was using the coordinate in the 0 page to put a stone there, but when I was printing stuff, it did not print the stone in place, and that happened because if before the stone we have a square that is not equal to 2e or whatever non-zero value, then print routine would just drop that. Hence, the stone would be placed in a wrong place. But yeah, that's just a matter of how my emulators are working. So when the board is filled with the period, so this is the ASCII code for a period, and in this case I can put the stone to the desired coordinate. I will show you this in this video, and it then works nicely. Okay, so another update, I created two more functions. One function to essentially fill up the board with this period, 2e ASCII character, and another function to print columns and rows. So let's scroll down a little bit. Another interesting thing here. So I was forced to add one more instruction to the print board routine, which is the clear the carry flag, because otherwise it wasn't jumping here after I did some manipulations with the carry flag unintentionally, but it happened. So seemingly my print board function was broken, so I needed to add this one little instruction. This made me changing all the addresses in the listing, but in the actual source code, I needed only to change a couple of bytes. Well, essentially these two, but I didn't even show you this one and this one. So where the absolute address of where the coordinates are stored. So let's have a quick look what the clear board does. So just right after the print board, we have the clear board. So same thing, using the X register as the counter. So we loop over the entire board until we reach the value of FF. Then it wraps around, then the 0 flags get set. Then we just return. Otherwise, we just loading the value of 2e into the A register and storing it into the 0 page index by X, efficiently filling the entire board with the value of 2e, which is the ASCII code of the period. Then we want somehow to print the coordinates. So I decided that storing coordinates essentially takes less bytes. So this entire thing with coordinate bytes being stored with the clear board and with the print coordinates routine, it's still less than 117 bytes, which I initially used just to print the board with all this stuff. So it's still more efficient, although it takes quite a lot now, but anyway. So this is just a variable. It contains the values from 0 to F. So these are the ASCII codes for these characters 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So what we want to do is very simple. So essentially we just loop over the so X registers a counter. We loop 16 times. Hexadecimal 10, but 16 in decimal. So every time we increment X counter, like before this, we just load from the absolute address of the coordinates. So A register gets loaded with the value of this 0, 1, 2. Characters, not the value of 30, value of 31, And then we store it into the 0 page indexed by x, so to the cells like 0, 1, 2, 3, 4, etc. Then we increment x, and when we run out of these characters, then we go for another loop. And a loop to print rows is essentially similar to the above. The difference is that here we're using the y register as a counter. And then for x, we just do add 16 to our x register every time, every iteration in a loop, in order to point to the proper location. So we want the values of 0, 0, 10, 20, hexadecimal, 30, hexadecimal, 40, 50, 60, 70, 80, 90, A0, B0, E0, D0, E0, F0 to be equal to whatever of these values. And at the end, we are getting the board like filled with both like empty squares and also the coordinates. And then the print board function will simply print the entire board as if it was a single string. I will first show you how this works in my KIM-1 emulator for Linux, and then same but on a smartphone in the mobile version. So I already have the paper tape for this exact listing that we've just seen in the clipboard. So I just paste things in. And now if I go to 0200, so these are the codes that we just had a look at, but the driver code is located as 0300 hexadecimal 300s. So here we start with clearing the decimal flag, which has to be done once in literally every program if you don't want the add with carry and subtract with carry work in a weird way, like with binary coded decimals, but in a normal hexadecimal way. So we need to do this, clear the decimal flag. So then we, so 21F02 calls the clear board, then 203902 clears, calls the, we call it print coordinate, but essentially it's not print, it's just like wondering, should I really call it print coordinate? P chord, we may think of this as put coordinate, not really print, but put the coordinate. Anyway, so this routine will put the values of coordinates, ASCII values of the coordinates to the 0 page appropriately. And after this, 200002 would call the print board. And I'm wondering, I have one extra bit that is not needed really. 03 0A. Yeah, I need to fix this as well. Anyway, let's try to run. So G, and as you can see, we have a board here. And also, despite the fact that starting from here, these values are used by the KIM operating system. But since we are doing everything in one run, they get overwritten. So when the program is working, I can make use of the entire 0 page to serve for the purposes of the program. Then if I now have a look at what is there, the values will already be overwritten, but by the time the program is running, it's totally fine to use those values. And also we have these nice coordinates being printed, just like in the original photo in the Byte magazine, where John K. Miller has been showing his terminal, the monitor of his terminal, like the entire terminal, yeah. Okay, let's now try to put some stones. Oh my goodness, if I could only remember the... yeah, I need to reference my codes here. Oh my goodness, where is... I forgot the codes for... Oh yeah, here are they. Yeah, essentially, I can also reference the codes for stones in here. have the codes for stones in here. So 23 stands for black stone. So if you want to put the black stone here, the 3 point, so this is like 0, 1, 2, 3, 0, 1, 2, 3. So we don't care about zeros. Essentially, 33. If we go to 0, 0, 33, and currently there is a period, an empty space, but we want to put 23 there. And if I did everything properly, if we now print, it's not going to work like this because it will override things. So yeah, unfortunately, it would just override things. The stone should appear here, but it won't appear there because, yeah, we just overwrite things. So let's go to 0, 3. So here, before, yeah, so 0, 3, 0, 7. Okay. So here we can do A9, which is LDA, and the value of 23. SDA to 33. And then let's say SDA to say this one. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, D0, D1, D2, D3. So D3. Okay. And now I want to print the board. So 20, 0, 0, 0, 2. Okay. So if I do everything properly, now this stone as well as this stone should be placed on board. Hold my breath and try to run things. And whoa, yeah, we have the stones here. Cool, isn't it? So this is now like very convenient. So you want to put the stone at 3, 3, and you can just use the memory cell 3, 3. You need to make sure that first you use the row and then the coordinate because of the board and the NS. Anyway, yeah, say you want to put like B, B, C. If you put there, that would be a stone. So it's very efficient in terms of when it comes to passing user input. So we don't need to do any. So we don't need to do any additional math. So we don't need we don't need to do any additional calculations to convert the user input into a coordinate on board, and that's the original design solution by xiangqi and Millen from back in the day. So yeah, this is really cool, and I think this was done exactly this way because I cannot imagine how this can be done better. Anyway, this is it in regards to the KIM-1 emulator for Linux. But what is even more interesting, I just want to show you the how this works in the environment where I have been developing these two functions. So these two functions, I've been developing them yesterday and today. So this function, clear board, and this function, put coordinate into the 0 page. I need to change this to put coordinates. Okay, I'll do this later. So all these opcodes, well, I put them on paper with a pen, obviously, but then I wasn't using this emulator to test like I did before. So now I was entirely developing on a smartphone. So I will now show you how this worked. Okay, so here is my emulator. Now we can load and save paper tapes. So I just paste paper tape from the clipboard. This is exactly the same paper tape that we just had a look at. And I click load, and it automatically fetches the address where it should be loaded. Now let's go full screen. So 0, 2, 0, 0, and yeah, so the start, clearing the carry flag, 18, and further on, so 0, 3, 0, 0, D8, yeah, clear decimal flag. So here is where the driver code starts. So if I just say go, essentially prints the board quite nicely. Yeah, cool, isn't it? And exactly the same way we could set up some stones. So let's try that just for fun. So 0, 3, 0, 0. And I just go to here before I go into data mode. Before printing the board, I want to say A9, which is LDA, and then 23, which is the hash symbol, ASCII code of a hash symbol representing the black stone. And then we want to say 85 STA to the 0 page at address 33, 33, and then 85 to the address of D3, yeah, D3. Okay, going back to data mode, I just want to check this out one last time. So, okay, and load into accumulator the immediate value of 23, set the accumulator to the 0 page address 33, and set the accumulator to the 0 page address D3. Yeah, okay, and I didn't print the board after. Okay, 0, 3, 0, 0, one more time. Yeah, I forgot to print the board after. So A9, yeah, this, and here, yeah, it's going to data mode. So 20 and 0, 0 and 0, 2, print the board. Go into address mode, 0, 3, 0, 0, and go. And yeah, now we got our stones. So 3, 3, one stone and another stone. Yeah, so now this works like a charm. And we had some inputs from the previous output, but it doesn't really matter that much. So we have the stones been printing quite nicely here. So yeah, guys, this is it from my side. Thanks for watching. Next step is to start working on the count routine that would be looking for connected stones in a group, and that would be a recursive function, a hell lot of debugging. But with this nice little KIM-1 emulator that runs on my smartphone, I really enjoy the development progress, and it's really like nice and cool. I don't even need my computer to be turned off. Like, laptop is like having some rest while I'm developing, so I just write the code on a paper, and then I'm using this emulator to debug. And then when, say, I want the update, yeah, if I want the update, I can just go back and here I just select all, and I just delete this. I can also save the paper tape from the address 0 to 0, 0, okay, and up to 0, 4, 0, 0, okay, and I just, okay, I already click save, yeah. So this is the updated paper tape. It's not seen nicely, it's quite small, but I can copy this and I can store it on GitHub or wherever. So copy this somewhere, and then I can write this, then I can load this exact paper tape, the fixed one or the one that now contains more features, like new functions. I can run it on my KIM-1 emulator for Linux. So yeah, it's really convenient when I can use the paper tape format to make the program like portable from one emulator to another. Yeah, this is it from my side. So thanks for watching again. And yeah, hopefully we are going to see the count routine being implemented by the next video. But it may take time because it's quite a complicated task to achieve. But anyway, I'll try to share with you guys. Yeah, thanks for watching again. See you later and cheers.